If you want to learn how to design your own custom PCB, then this video is for you. This video is really the second part of an in-depth PCB design tutorial. And last week I shared the first video on how to design the actual custom PCB layout itself. And you can see the link for the first video in the description below, or you can click on the card in the top right corner of this video. Now in the second video, you'll learn how to run proper verifications on the PCB layout to ensure there are no design errors and that it precisely matches the schematic. And then finally, you'll learn how to output the design files for ordering boards. Hi, I'm John Teal. I'm an electronics engineer and a former microchip designer. And I also brought my own hardware product to market, which was sold in hundreds of retail stores. Now I help other entrepreneurs succeed with their own new products. Okay, let's get started. Here is our design where we left it, and now we're going to run the various verification steps to make sure the design is good. If you indip trace at the very top, you'll see a verification menu, and there are three types of verification that we're going to run. The first one is a design rules, or a DRC, design rules check. And what it's going to do is mainly it's going to just look at the PCB rules, like what is the spacing allowed from one trace to the other? What's the minimum width of a trace? So those types of physical layout rules, that's what that's going to check. Then next, there'll be a check at net connectivity, which is going to make sure that all the right devices and pins are connected up to each net. For example, the I2C pins, that should go there on that net, the I2C net. On that net, there should be one pin for the accelerometer, one pin for the microcontroller, and then one pin for the pull-up resistor. So that check is just going to make sure that all those devices are actually on that net. And then the final check verification is to compare it to the schematic, just to make sure that the full PCB layout design matches the design in the schematic circuit diagram. Okay, we're going to go ahead and let's run a check design rules verification. We'll get into the design rules in just a second. Let me just run this here real quick and see what errors we have. Okay, the only errors that we have right now are all around this U3. And for the most part, we're going to ignore them. We have a minimum spacing rule from SMD, so a surface mount device. These are surface mount devices. They're not like a through hole. They don't have pins that go to the other side of the board. They're just all on one surface. So these are SMD is what they're called. And this is what we're violating is the spacing between these pads. We have the rule set at 6 mils as the minimum, and which is what this package should be at 6 mils here, but it's actually measuring 5.91. So almost 6 mils. So what we're going to do is I'm going to go in, we're going to take a look at the design rules now. And these are all the rules that we're just for the most part for this tutorial, we're leaving them at their default value, but you want to make sure that you have all of these design rules set that matches the rules for the specific process that you're using with your specific PCB manufacturer. So you kind of have the rules broken into two parts. You have clearances, which is the error that we're hitting. So clearances, trace to trace, pad to pad clearances. And then there's also sizes. So like the minimum trace that we're allowing is 6 mils, etc. Minimum drill size, things like that. So that's under sizes here. So the rule here that's giving us the trouble is the SMD, surface mount device, to SMD. So pad to pad basically on an SMT device. But what I'm going to do is we could easily just use a process that had a 5 mil clearance, which is a common clearance that you can use. In that case, we would just change almost all of these to 5. But just to simplify things, I'm going to because honestly, 5.91 mils is so close to 6 mils that I think it would be okay even with a 6 mil minimum process. But just to make this error go away so it doesn't trip us up too much, I'm just going to change this to 5.9. So just barely under the 5.91 that it's measuring. Okay. And if this were a real design that I was going to go into production with, then I would spend a little more time probably fixing this here. So if I wanted to go with the 6 mil, if everything else was going to be a 6 mil clearance, and this was the only thing that was causing me a problem, then I would go in and fix this a little bit better. But for this tutorial, I don't want to focus too much on it. So now that we've changed the design rule for that, I'm going to rerun the design rules check, and there are no errors found. And let me just show you another. I'm gonna clear the copper because I want to change something. I just kind of want to show you another example of an error being generated. Let's say I have this trace here too close to this capacitor here. So I'm just going to get it like that. And now I'm going to rerun. And now you can see we're getting an error here on both the wire to this pad and to this pad. It's saying it's measuring 5.91 or 5.94, and the rule is 6, so it's below the rule. Now it's down to 2.94, and it's supposed to be 6. So I'm going to just pull this back down here. So we're there. Okay, now we're back to a clean design. So now I'm going to go and turn back on. I'm going to update all the copper pores. Next, we're going to run a check net connectivity, and this is typically where it requires a little bit of work. And yes, we wanted to check everything. We're not using shapes for any routing, but in this design, we do have traces and copper pores. So we want it to check with all of those being methods of connection. And as fairly typical, we have some errors in the ground and in the supply. If you can see here, it's saying ground. Let's focus on ground. It says ground is broken into 3 areas. When I click on that, you can see it's showing 3 areas. So it basically means that you can see most of the devices are in area 1, but area 2 has its own device, and area 3 has its own device and pin. So that means that U3, pin 3, and C4, pin 2 are not connected to ground. So we're going to focus on looking at those devices. So I'm going to go and do a find object, and let's just do U3, which I know is the accelerometer, and it was U3 pin 3. So that is this pin right here is the problem. And this is, you can see what happened is the copper pore, because of the rules on the copper pore, it couldn't get in there tight enough to make a connection to this pin. And this pin is not really not a ground pin of this accelerometer. It's one of the input pins that just needs to be grounded. So it can be routed easily. It doesn't need to have a really solid ground connection. So what we're going to do is I'm going to turn off clear the copper pore. And I'm going to drag this over here. And I'm just going to route up this pin. Here, let me remove some of these windows out of the way here. So we're just going to route. We just need to connect this to ground. Easiest thing is just go over here and grab this ground via. Okay. Next we have C4. So I'm going to do a search on C4. And C4 is this device here. Let's see what's happening. We're going to turn back on the copper pore so we can see what's happening. Okay, see what's happened is there's been a copper pore in this area here, but it's isolated. Because of this wire here, this trace here, it couldn't connect in with the other copper pore. And it's just, it's connected to these capacitors, but it's still floating. So there's 2 options we could do. We could change this routing here, maybe switch it to the other side of the board so the copper pore can just connect. Or a better solution is I'm going to clear the copper pore, and we're just going to add a couple static vias here. Because remember, we have a ground plane underneath, so we can just via down and connect to that. So I'm going to go under here, place static via. I can just maybe do 2 of them, would be fine. And I select both of them, right click, add to net, selected vias, select the net ground, that's already selected. And now you can see everything highlights. So now when I go back up and update the copper pores, now these vias connect this ground to the ground plane underneath. So let me close that, and let me close that, and let's rerun our net connectivity. And yeah, so now our ground issues are all solved. All we have left are the supply rail, the 1.8 VDD is not making it everywhere. Okay, so I'm going to go back and I'm going to just do a Control F. And for find component, we're going to look for R1. There's R1. I'm going to turn off the copper pores because I have to do some routing. And let's see here, we have R1, which needs to go to, this is just a pull-up resistor. So the routing isn't critical. And I'm just going to route this up here. Tie it to the supply. Okay, so that's R1. Then it's showing R3 also here. And this is the other pull-up resistor. And we can just tie that here. And then we're also, see, this is C13, I believe. C13 is C13 is here. So what's happening is, okay, I've tied this together, but these three now are connected, but they don't connect to the full VDD. So now I'm going to just connect, let me just, and we'll just tie that there. This is the VDD IO for the accelerometer, and this is the normal VDD. They're the same on this design, so I can just tie this together. Okay, now you always have to make sure you update the copper port, because let's run it without the copper port, and you'll see all these ground errors because nothing is grounded because you don't have the copper pores. So I'm going to go in here, update all copper pores, and rerun the, oops, that was the DRC. That's still clean, that's good. Now check net connectivity. Okay, so we fixed the positive power supply rail, but we've done something that's now messed up the ground. So we have some ground isolation. And it's saying U3, 5, 6, 7, and 8. Okay, so what's happened is now all these pins are connected together by this copper pore. But because I routed this line over now, to connect up this pull-up resistor to the supply, we've isolated this away. And what I'm going to do is I'm going to do exactly like I had done before. And let's turn off copper pores, and we're just at a static via. I'm just going to do one via is sufficient. Select it, right click, select from list because I only have one of them, and ground. There, okay. Now let's update the copper pores again. Let's go ahead and run the DRC. Yep, we didn't create any new design rules errors. And check net connectivity. No errors found. Okay, now we're getting some way. And then the last check is compare to schematic. So I'm going to compare it to my final schematic. And no errors have been found there. So we have a totally clean design now. We have no design rules errors. We have all the nets are connected properly, and the PCB matches the schematic. Now, the only step left that I want to do before we output the design files is fix the reference designators, which are over, you don't want those over any pads. So we're going to go through and fix that. These are the reference designators, C4, C5, U1, such, and these are all printed on their own layer on the PCB called a silk screen. So any text that you have will be printed on this silk screen. And what will happen is if you can have them over metal, it's like this C4 here is okay. That's not a problem. You can have them over traces and copper pores. But what you can't have is you can't have them over exposed copper because that needs to be a solid connection. So any of the pads at all, you cannot have any reference designator or silkscreen text over it. And this can be picked up as an error by design rules check. We just had it turned off. So I'm going to turn that on now. Go under design rules. Then you'll go under this options here and check this here. Check silk over pads. And the clearance isn't critical, like I said, or this isn't going to cause any functionality problems. So if the silk screen or your reference designator goes over the pad, it's just not going to print that text and you're not going to be able to see it, but it's not going to cause any design issues. Therefore, this clearance isn't super critical. I'm not sure what the default is, but 1 or 2 mils should be sufficient. Okay. Now we've got that rules turned on, so now I'm going to do a new check design rules again, and we'll find a bunch of new errors. And it's showing you all these errors here for the silk screen. The solution to this is we need to move the reference designators around and get them off of the pads. And to do that in dip trace, you're going to just press F10, and then that allows you to go around and move any of the reference designators or reference designators only. Okay, so I'm going to do an F10, and now I can, oops, there we go. Okay, now I just move around the reference designator without moving the device. This C4 one's okay. It's a C5 that's a problem. So let's move it over here because this is really C5 here. This is C4. This U1's not a problem where it's at, but it's for this chip here. So I would move it up here, and it's kind of in a random spot here. So I'm going to just right click on that, rotate it around, and move that up here. Okay, let's rerun the check. That got rid of that one. Let's go to the next one. Just double click on it. C7 is this capacitor here. So for that one, we could just do here. C8's okay, but I'll still move it. So to pad. Okay, there we go. And C7, because I have the 2 mil spacing, it's still over the pad. I didn't realize that the pad was right that far up. So we're going to move this a little bit there. Okay, that got rid of that one. And now let's go to the next one. Just double click on them, takes you to the next one. And we have this reference designator here. I'm going to move that up here. And C12. Okay, so C12 is this. This is C11. Let's move C11 over near its capacitor. C12, I'll just move here. C2 is okay. Rerun. Okay, we're down to just 3. Let's double click on this one. Oh, we got a problem here. Let's move that down. Rerun. Now we're down to 2. Here. Oh, yeah, this one I'm not. This one, don't worry about. This is it's not text. It's just the silkscreen layer for this crystal that shows the outline, and the outline in their design. This is from the library. It just runs over the pad. So this isn't critical at all. All that will happen is this part of the line will not print. So we're going to skip that one, and then this one is the same way. Okay, so we can skip both of those. Okay, so now we've fixed all of our reference designator issues. I'm going to go ahead and I'm going to turn this back off because I like to see that says no errors found. And we determined those two, or for the crystal, the silk overlapping the pad wasn't an issue. And let's do check connectivity, make sure we didn't break anything. No. And check the schematic one last time. Everything is good. Okay, we have a clean design, and now we're going to output the design file so you can order boards if you wanted. In most cases, I wouldn't recommend that you order this board. It doesn't really have a whole lot of functionality, but I want to obviously show you the process for ordering boards so that you can order boards once you do your own custom design. So what we're going to do is go under File, and everything we're going to do is under Export. There are 4 main groups or types of files that we're going to have, or 4 files that we're going to have to output. First of all, we're going to output what are called Gerber files, and that will be a separate file for each layer of the printed circuit board. So there'll be like a silkscreen layer, there'll be a layer 1, a layer 2, etc. So those are the Gerber files, and I'll just output multiple files. Then we also have what's called an NC drill file, and what this shows is a document or a file that gives the coordinates of all the via holes and any mounting holes. So basically any holes, what size drill they have to use, because these are holes that are actually drilled through the printed circuit board. So that's the drill file. Then we also have a pick and place file, and a pick and place file is for automated PCB assembly. So it tells the machine the XY coordinates of each component on here so that they're placed in accurately on the right location and matched up with the pads. And then finally, we have a bill of materials, which is just going to be a spreadsheet that lists all the components and their part numbers and their quantities. Okay, we're going to start here. We're going to do Gerber. And you can see here it shows the various layers. Not going to go through all the different layers that we have here. We're not using all of these layers, but what we're going to do, and just leave everything here as default, and we're going to do export all. And what I'm going to do, instead of exporting each one separately, I'm going to export a zip file that will include all the Gerber files plus the NC drill file. So this is sort of 2 steps in one. And we'll just call this, let me call it Gerber's and drill, like that. Okay. Okay, so we have that. Let's take a look at that now. And here's our zip file. I'm going to go ahead and extract it. And here's what's in that zip file. You can see these are all the Gerber files that it generated. And then this is the drill file, the .drl. And there's only one because we're using only through vias that go through the entire layer, or the entire board. Regardless of how many layers you have, a through via goes through the entire board, and that's in most cases the type of vias that you'll use. So there's the drill file for that. Okay, we're going to go back. I'm going to delete this BOM because we want to generate a new one. Okay, so we have the Gerbers and the drill file. Let's go back under export. Now we need the pick and place file that gives all the coordinates of all the components. And I'm just going to leave all the defaults. We're going to export to a file. And I'm going to name this, I'll name it pick and place. And it's a CSV file. And I'm going to use the column divider as a comma. And I don't think that, normally I leave this on actually. So we're going to leave that on. And you may have to, if your PCB manufacturer tells you, you may have to regenerate this based on what they require, but typically this is how I've always done it. Okay, now let's go back under Gerbers, and now we have a pick and place file. Slow to open. And now you can see that it gives all the components and it gives their X and Y coordinates. Okay, so that's the pick and place file. And then the only thing left is to output the BOM, which is bill of materials here. And once again, we're going to export to a file. I'm just going to call it BOM. Outputs to a CSV file. We'll leave this alone. I don't use quotation marks for values in the BOM. Okay, now let's take a look at that. Created the BOM. And what it does is it just numbers the components, but it gives you the name or the part number and the quantity. And there are some errors here, and I'll explain this. You can see it's saying we have 13 4.7 microfarad caps, and that is because from the schematic. This all comes from the schematic, and the only thing that it will affect is the bill of materials. So let me open up the schematic again. And the reason we're getting that is because I've not gone through here. We kind of just copied these capacitors around, but what you really need to do, and I'm not going to do it necessarily now, is we would go through and we would actually have to go to like Digikey and find 10 microfarad capacitors. Here we would put the part number. So let's just say 10 microfarad part number. Here we would do, this one is 100 nanofarad, so I could say I would go and find a 100 nanofarad capacitor that's the right size, and these are all 0603 surface mount capacitors. And let's just say part number there. But basically, to get the BOM right, you have to go back to your schematic, and usually the chips are all okay because we've selected those from the library, so those have the part numbers. This one even has the Digikey part number, which is usually the electronics component distributor that I have always used is Digikey. But it's mainly the capacitors and any of the other passive components like the resistor. Let's see. Yeah, it doesn't even have a part number here. So we would have to look up the part number for a resistor, a 10K resistor, that's an 0603, and we would put that here. And then you would go back in and you could regenerate the not the printed circuit board layout, but regenerate the BOM, and then it would have all the right part numbers. That is everything there is to outputting the design files. Okay, that is it for this two-part tutorial on how to design and verify a custom PCB design. I'm John Teal with Predictable Designs, and I hope you have found this video helpful, and I hope you have a great day. Hey there, this is John Teal, founder of Predictable Designs. If you enjoyed this video and you want to keep learning more about developing, manufacturing, and selling new hardware products, then be sure to subscribe to our YouTube channel and also check out the websites predictabledesigns.com and thehardwareacademy.com.